They're expensive too. They're like $25 for one big book. Really?
Okay, today we're going to start related rates, also known as word problems, also known as fun and excitement. Pretty much a quick introduction and then example after example after example after example, because related rates fit into categories, and once we establish those categories, then it's just a matter of modeling each problem after another problem. So, we're going to need to find a related rate. The biggest difference now is that everything is going to relate to time. So we've taken a derivative of y with respect to x, that's the dy dx thing. We've done the derivative of x with respect to x, that's dx over dx, which we never talk about. But now we're going to start taking derivatives of everything with respect to time. I'm going to show you a 9-step approach that has proven fairly successful for people getting this thing under control. And then, of course, for today, you should enjoy spicy food. Yeah, he brought in spicy food. Okay, so here we go. We have already talked about how to find the derivative by taking implicit differentiation. That's when we find dy dx. But as I mentioned earlier, we're going to change that to dy dt, dx dt, dz dt, d whatever dt, because everything is going to be related to time. Okay? So we'll start with this. I've got a nice little function here. It's already in y equals form, which makes my life a little bit easier, but it doesn't really matter. I don't have to bother trying to solve it for y, because now we know how to do implicit differentiation. First things first is they're differentiable functions, which means we can take the derivative of both of them. That's an important part of the problem. Okay? We want to find dy dt. We want the derivative of y with respect to time when x equals 1, given that dx dt equals 2 and x equals 1. Okay. Now that doesn't seem to make much sense, but as you see me work through the problem, you'll understand. This does not require a 9-step approach. It's just a matter of taking the derivative. So what's the derivative of y? Now, correct, y prime, but remember y prime stands for dy dx. We're not doing dy dx anymore, so we can't just use y prime. We have to use dy dt. So the left-hand side of that equation becomes dy dt. What about the right-hand side? 2x dx dt, because again, t is our variable, not x or y. If we were taking x as our variable, then the derivative of x squared would just be 2x. And then the derivative of 3 is 0. So we get something like that. Right? That's step one. And all I'm saying in that case is I'm going to take the derivative of the left-hand side with respect to t and take the derivative of the right-hand side with respect to t. Then I actually do that and we get those values you just talked about. How many unknowns in that last equation? Which one? 3 or 2? No, which one? 3 or 2? There's 3. dy dt, x, and dx dt. Basic rule of algebra, if I want to solve an equation with 3 unknowns, how many of those do I need to know in order to be able to solve it? 2. Got to be able to solve 2. Well, what do I know from the problem? I'm looking for dy dt when x equals 1, so I know what x is. I know what dx dt is. Plug and chug and solve. Easy problem. We get 4. Because 2 times 1 times 2 is equal to 4. That's not so bad, right? That's called a naked related rates problem. It's called naked because it doesn't tie into any real world situations. That's the first type. Here's a function. Take the derivative of that function with respect to time. Plug and chug, good to go. Okay, but that's no fun. As I've mentioned the last couple of days, we want to look at things that involve death and destruction. Falling off of ladders, crashing cars, crashing airplanes, etc., etc., etc. Leaky buckets, all kinds of fun stuff like that. What do I got? Leaky containers, racing automobiles, falling ladders, police sirens, there's one like that. A couple others. All right. Let's do this. Here's the 9-step approach. If you don't want to use the 9-step approach, it's okay. It's not mandatory. If you sit down at the AP test and you ask the supervisor, excuse me, do we need to use the 9-step approach? College Board has no idea what the 9-step approach is. It's just a method that we came up with to help you solve these problems. Okay, step number 1, draw a picture. And label that picture so that the person reading the problem knows what the heck you're talking about. Step 2, define the variables. Sometimes in the problem you'll have to create the variables. Okay, I'm falling off a ladder. What do I need to know? Well, my height. What do you want to use to represent height? We'll usually use h to represent height, but you should tell the reader, the grader, the person that's looking at your problem, what each of those variables represent. Step 3, what do you know and what are you looking for? And some of these aren't going to make much sense until we get into the actual problems. Step 4, write a general equation. And notice in red it says, do not plug and chug yet. That's a big mistake that people make early on. So don't do it. That's why it's in red. Step 4, or sorry, I have trouble with numbers. Step 5, take the derivative. Strangely enough, that's usually the easiest part of the problem. The equations that we use don't get that complicated. Step 6, snapshot. At that exact moment of time, what's happening? You're falling off a ladder. 1 second after you start to fall, what about blah, 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 blah? 2 cars are heading towards the same intersection. They both leave at noon. What happens at 12:15? Step 7, solve. A little bit of algebra going on there. And then steps 8 and 9, clean things up. Does your answer make sense? Sometimes you won't be able to answer that question. Other times you will. You know, if you're calculating how fast a car is going and you get 3 times the speed of light, you probably did something wrong. If you're calculating the change in the weight of a, I don't know, whatever, a baby elephant, okay, and you get something like 743 tons, it's probably not right. So take 2 seconds and just see, does your answer make sense? More realistically, you're going to get an answer like you're calculating the rate at which you're sliding down a ladder. Your answer should be negative. Did you get a negative answer? And then step 9 is include units. What are we talking about here? Are we talking meters per second, mile per hour, donkeys per circus, whatever it is we're dealing with? Okay, you ready for this fun? This is going to be a blast. We'll start with something easy. We're going to inflate a balloon. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Now the weird thing is everything that you need is in those 2 sentences. What you have to do is decipher all of that fun stuff. So I broke this problem down step by step for you, and then the future examples we'll do our own breaking down. Okay, draw a picture. Maybe something like that. If you want to get all fancies in your panties and make it look like a sphere, then by all means, knock yourself out. You want to put that little circle in there. You want to shade it. Doesn't matter none to me. The only thing I care about in that thing is the radius. So therefore, step 2 is to find the variables. 2 things I care about in this problem. The radius, which I'm calling R, and the volume, which I'm calling capital V. One of the great things about this country, you can do whatever you want. If you don't like R and V, change it. You want to use Q and a picture of a small goat? Go ahead. I don't care. That's why you're defining the variables, though. If you choose to use a small picture of a goat, then the reader knows that the small picture of a goat represents the volume. Not something I'd suggest, but again, God bless America is correct. What do we know and what are we looking for? It tells you how much air is being pumped into the balloon. That becomes the change in volume. So dV dt is 4.5. It's positive because the value is getting bigger. If the value is getting smaller, it would be negative. So you could ask the same problem, but the balloon is leaking. The bucket is leaking. If the quantity is going down, the rate is negative. And what are we looking for? I'd like to know what's the rate of change of the radius when r equals 2. Have I lost anybody yet? Pretty easy so far? You good? Kaylee, okay?
Yeah.
What was that little dance move?
No, that's good.
Okay. The dance move was good, or this is good?
We're okay.
Okay. Let's move on, shall we? Step 4. What's a general equation? What are we dealing with? What about the sphere?
Volume.
Volume. Do you remember the volume of the sphere? No. You don't have to. I got it right there. So you're saying to yourself, self, do I have to remember all those crazy geometric volume formulas? No, you don't. 3-dimensional geometric figures will be given to you on the AP test. However, you do need to know simple things like the area of a circle, area of a triangle, the Pythagorean theorem. But anything that's 3-dimensional, a sphere, a cone, a cylinder, they will give you the formula for them. That's it.
Cilantro? Salad?
Right. Formula for a salamander. Szechuan? Yeah. Step 5. Take the derivative. I don't know if anybody has done this yet, but have you noticed how funny it is when you take the derivative of the volume of a sphere? Anybody do this weekend, just hanging out with your friends? Hey, let's take the derivative of the volume of a sphere. What do you get? What's the derivative of 4/3 pi r cubed? 4 pi r squared. What is that? Yeah, it's the surface area. So strangely enough, the surface area of, the derivative of the volume of a sphere is the surface area of that sphere. Ooh, that's cool. Let's take a second and make sure, is everybody okay with that derivative right there? Derivative of v is 1 dv dt. The derivative of 4/3 pi r cubed, bring the power down, 4/3 times 3 is 4. Pi is a constant, so it just sits there, reduce the power by 1 r squared. I took the derivative of r with respect to time, so I've got to stick a dr dt on the end of that. How many unknowns in that what is that thing called? Equation. 2, 3, 4. 4, 3, 1, 9. Szechuan? 3, salamander. There are 3, dv dt, r, and dr dt. Hopefully, if we want to finish this problem, which it would be kind of sick and twisted if I gave you a problem that couldn't be finished, we should be able to finish this problem. Okay. So now we do the snapshot. In other words, early on in the problem, you might be tempted to put 2 in for r, because it tells you in the problem that r equals 2. You want to stay away from that. Okay, we want a general statement for all points in time, and then when we get to step 6 for the snapshot, we're looking that exact moment in time when r equals 2. We're looking for dr dt. We know r is 2. We know dv dt is 4.5. Plug and chug. Which is step 7, which is solve. Did I go too fast?
No, would it ever give you like the dt? Like if it gave you dv over dt and dt and you have to find r and dr, would it do that or no?
No. No, the DVDT, the DRDT, those are all considered one. They're like peanut butter and jelly. You seldomly, if ever, separate.
You're like peanut butter guy.
Yeah.
It's so weird, right? Air fire measure. Nobody separates them. It's almost just a jelly sandwich. Did you say it's butter sandwich? Okay, wait, butter and jelly? Yeah, just butter. Butter and jelly, all right, let's bring it back together. Sorry. Obviously, I want to try and keep this a little bit more on task here. 0.09. Does that answer make any sense? Ben, do you have any idea about the rate at which radius increases when you're inflating a balloon? Have you done a lot of balloon inflating, Ben?
No.
No, me neither. Do you trust my math?
Yes.
You're a sucker. It is right. What are the units? Now I'll show you a trick to recall not to recall, but to figure out the units. Notice that I solved for DRDT. I want to find the units on that answer. What are the units on R? Was it? I don't remember. Was it feet?
Yeah.
What's the unit of time? Seconds. Minutes? There's some discrepancy. Okay, so then your units become feet per minute. So you can use the thing that you're solving for to come up with your units. And it is feet per minute. All done. That wasn't so bad, was it? Come on. That's just number 2. Let's take a look at number 3. Now, to make your life a little bit easier, and so you don't have to write so much, you have 2 options here. 3 options. Option number 1, you could write like a mad person and try and keep up. Option 2, I have a paper copy of the next 3 examples we're going to do, and you could write on that. Option 3, I converted this into a PDF, which is on Schoology. Choose one and let's rock and roll. Paper? Paper. Who wants paper? Paper. I'll come to you. I get nervous when people start charging me. Paper. Change his mind. 1, 2, 3, 4. Paper. 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 Digital. Yeah. Paper. Paper. Digital. Paper. Paper. Yeah, why is it? Digital. Digital. Paper. 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 Digital. Digital. Beautiful. As I mentioned, you don't have to know the formula for the volume of a cone. So we got a leaky cone. And that volume is pi over 3 times r squared times h. Notice all of a sudden I've introduced a new variable. The sphere only had one variable, and that's the radius. However, the volume of the cone has 2 variables, r and h. Okay, so there's our problem. The water tank in the shape of an inverted right circular cone has a height of 12 inches, or 5 inches, or 10, but good. There is a little conversion there. You've all had chemistry, yes? You understand the concept of density, yes? Liquids weigh different amounts. That becomes relevant. Do you need to remember the density of water? Well, the density of water if you want, but do you need to remember how much a gallon of water, or what the volume of a gallon of water is? No. If there's anything that needs to be converted like that, it'll be given to you. However, water pops up a lot. It's 0.1337. There's my cone. water, cone. Okay, so let's go. Let's do this. There's my picture. I already identified my variables. What does R stand for? Radius. What's H stand for? Height. Right? There we go. Notice radius of water, not radius of cone and height of cone. They're different values. Step 2. What do we know? No, that's step 2. Step 3. Yes? What do we know? What are we looking for? So in that paragraph at the top, what does that tell me? Know the height and the radius, very good. What else do we know? Okay, what is that rate? Is it positive or negative? Positive, because the volume is getting larger as you pump it in. Okay, and we'll worry about the gallons per minute in a second. And then what are we looking for? Approximate the rate at which the water level is rising. What is that? How would you represent that mathematically?
Less between the water and the base.
You're thinking too much. Okay, this 10 is what? dV dt. What's this? What am I looking for here? The rate at which the water level is rising.
Height.
dH dt, right. The change in the height over time. And I want to know the change in the height, dH dt, when h is equal to 3. And notice I did the conversion there. 10 gallons per minute is the same thing as 1.337 cubic feet per minute. And we're looking for dH dt when h equals 3. That's step 4, right? Step 5. I believe, if I remember correctly, is it?
That was step 3.
That was step 3, right. Step 4 is
General equation.
general equation. What's the general equation? I gave that to you already. It's the volume.
Volume, yeah.
Okay, well this is going to ramp up pretty quick. There's 2 ways to do this problem. I don't like to use the words easy and hard, but I think there's one method that's quite a bit easier. I'm going to show you both, and you can interpret how you want to do it. So my next step is to take the derivative of that. What do you notice about the right side of that equation when I take the derivative? There's a product rule. You'll also notice that when I take that derivative with the product rule, I'm going to get an R and a dr dt. But if I go back, I don't know anything about dr and dt. It doesn't say anything about the radius in there. So that would require that I do a bunch of other work. However, there's another way to do it, which I'll show you first. And that is to do what I call a sidebar. Step off or step out of the regular problem, do a little calculation on the side, use that information and stick it back into the equation. In other words, I can get rid of one of those variables. And in fact, I'm going to get rid of the R. How do I do that? I got to do a little bit of geometry there. Remember this? What kind of triangles? Oh, first of all, how many triangles in that picture?
3.
1, 2.
2. The other one is it's a trapezoid. Yeah.
You're not wrong.
So, similar triangles. The blue triangle and the big white triangle allows us to set up an equation to get rid of one of the variables. Which one do I want to get rid of? Well, I already talked about the fact that I don't know anything about R or dr dt, so I'd like to get rid of the R. So I'm going to set up an equation first. I don't remember how I did it, but I could do R over 6 equals H over 12. Or I could do R over H equals 6 over 12. Again, I don't remember how I did it. Oh, I did it that way. 6 over 12 equals R over H. Okay, that's geometry, similar triangle stuff. Once I have this first equation, I could choose to solve that for H if I wanted to get rid of H in a different problem. This one, however, I already said I wanted to get rid of R because I don't know anything about it. Am I going too fast or are we okay? Everything makes sense so far? Okay, so all of this is what I call a sidebar. The only thing I need to get out of this calculation is I'm going to get rid of the r. Okay, so I know what r is in terms of h, so I can do a little substitution here. And that becomes that mess. 1/2 h in for r. I have to square it. And I get that guy. So it simplifies down to a pretty nice formula, or equation, I should say. Any problems there? 1/2 squared is 1/4. 1/4 times pi over 3 is pi over 12. H cubited. Oh, and that's an easy derivative, right? Was it? No, it's not. Question?
Can you open the sidebar again, like why you use it and like?
Yeah, because if I look at this equation here, the pi over 3 r squared h, I have two variables in there. One of which I don't know anything about. So if I wanted to find the derivative of that, I could do that, but I would have a product rule with a bunch of r's and dr dt's, which I know nothing about. So if I can come up with a sneaky way to get rid of the r's, then everything's in terms of h, and h is good to go. So I use the cross-sectional picture of my cone to set up some similar triangles. I guess I assumed too much. Is everybody okay with where that picture came from? Okay, good. All right, so we get that. What's the derivative of that equation? What's the left-hand side? dv dt on the left-hand side. What's the right-hand side? Beautiful. Pi over 4 h squared dh dt, which is right there. How many unknowns in that equation? 3. Do we know 2 of the 3? Yep. I don't remember what we know, but we do know a couple things. We know dv dt, and we know h. Yes, and we know h. Plug and chug.
That's something.
Had to convert to cubic feet per minute.
Because it says where the water is.
Oh, 3 gallons.
Yeah, gallons aren't usable. Doing a little bit of magic there, then I get 0.189 feet per minute. And again, in step 8, where you ask yourself, does that answer make any sense? I don't know. I don't frequently fill cones. But I do know my answer is positive, and I know that the height should be going up over time. So I'll call that a success. Okay, so let me take you through the other approach to this problem. I don't think anybody is going to use it, but I think it's important that you see how you would do the other problem. If, for instance, the similar triangles didn't make sense, or you just had a brain fart and you wanted to try something else, it would go something like this. I would take the derivative of that using a product rule, and now I've got a mess in there. I've got 1, 2, 3, 4, 5, 6 different variables, and I don't know a lot of those. So all I did there is clean it up, and then the next slide shows you how to deal with that. And again, you're not writing this down, so I'm just going to go through it. Using the similar triangle again, so you still have to use the similar triangles, I get that equation. And then you take the derivative of that equation to get that. I've lost you already, haven't I? Good. Don't use this method then. But I'll finish it just so I can say you saw it. Take the derivative of both sides. Now I can solve for dr dt. Plug that in, and I get where I need to go, where everything up all of a sudden in terms of dh dt. Okay. Not the ideal method, but is still doable. Still requires the similar triangles, though. Still requires an equation from the similar triangles, but I would just solve for the other variable first. Okay? Let's skip this one and go to the, where is it? To the ladder problem. Because this one's a little bit easier. We'll do the ladder problem, then we'll take a break and do some Treat Tuesday, and then we'll come back to the boats. A ladder 20 feet long leans against the wall of a vertical building. If the bottom of the ladder slides away from the building at a horizontal rate of 2 feet per second, how fast is the ladder sliding down the building? There is a common misconception that if the bottom of the ladder is sliding out at 2 feet per second, then the top of the ladder is sliding down at 2 feet per second, and that's not the case. We'll figure that out in a second. Now notice, I put 20 into the problem right away, because that never changes. If there is a value in the equation that is a constant, you can put that in right away. That's not considered violating the whole snapshot thing. It's just the ladder's not going to change as you fall. Has anybody ever been on a ladder when it falls? Oh, it's horrible. It's the most out of control feeling you'll ever experience. And there's nothing you can do except run your fingers down the building trying to stop it. Like that woman that falls down you've seen that video where the woman falls in the, no? Do you have any idea?
Where did she fall?
She falls in the hole, they're working behind they're in a store, and the woman opens the hatch to go down to the basement. And the woman doesn't see it and turns into it. No? I'll find it, I'll show it to you. Just not right now. Okay. Step one, draw a picture. I already got a picture. There's my ladder leaning up against the wall. The length of the ladder is 20 feet. I called the distance away from the bottom of the building X, because it's horizontal. And I called the vertical distance Y, because it's vertical. Step two, what do I know? Okay, what does this mean? Or how is that interpreted mathematically? 2 feet per second is what? Which one? dx dt. dx dt is equal to 2. Is that a positive or a negative value? Is x getting bigger or smaller as the ladder falls? Bigger, so therefore it should be positive. Okay. What are we looking for? How fast is the ladder sliding down the building? What is that? What is dy dt? dy dt equals question mark when y equals 12. Okay. What's step 3? So what did I miss? Oh, I forgot to define my variables. Sorry. X equals horizontal distance from building, as you can clearly see. Y equals vertical distance. Okay. Good. Okay, step 3, picture, identify variables. Step 3 we already did. Step 4. You can't read that? No. Horizontal distance from building, vertical distance.
Yeah, placeholder. Placeholder.
You guys blind? What's step 4?
Step 4.
General equation. What's my general equation here? Also, excuse me, also known as Pythagorean theorem. Step 5. Derivative. What's the derivative?
Oh no.
Nope. Remember, we're working in terms of t. I'll give you the 2x.
2x, okay.
2x. dx dt plus 2y dy dt dt equals 0. Beautiful. No y prime. Y prime again is dy dx. We don't want dy dx, we want dy dt.
So sorry.
If you want to get all fancies in your panties, divide everything by 2. Because what's 0 divided by 2?
0.
How many variables? 4. Do I know all 3? Oh, what's that? Another sidebar. When y equals 2, I get x squared plus y squared equals 20 squared. Therefore, x squared plus 12 squared is equal to 20 squared. I'm doing tag right there. What is that? Is that a 4? So it'd be 16? Yeah. 3, 4, 5 triangle? 3, 4, 5 triangle times 4? Or you could just crank it out on your calculator. 400 squared minus 144, take the square root of that.
So stuff with this level calculator.
Yeah. Oh yeah, almost all of these you're going to have to
We
calculate.
don't
Oh, gotta calculate.
X, and then we have the XC2.
Isn't that
Okay, well, that's 16 to 12.
Solve for dy dt, please. You'll need your calculators. Go ahead and get them out and do some calculations. Hence the reason they're called calculators. They do calculations. Before you do the calculation, will my answer be positive or negative? Negative. Why? Yep. The value of y is getting smaller. I don't think I mentioned this, but I will mention it now. The AP standard on problems is being accurate to 3 decimal places. If it's not accurate to 3 decimal places, they will mark it wrong. So if you have 2.665, they'll mark it wrong. They will, however, accept 2.666 because you can either round or truncate. Have we talked about this yet?
Yeah.
Okay, good. What are my units? You sure?
No.
Yes.
Y is measured in what unit? Y is measured in feet. Time is measured in seconds, so feet per second. Okay. And notice that my initial statement is true. Even though the bottom of the ladder is sliding out at 2 feet per second, the top of the ladder is moving down faster. Okay? We got one more to do. Wait, hold on. After we take a break.
Watch it be spicy though.
I